strategy. Okay? So I looked at these vectors, and I looked at the first components. That's what I do first. I look at the first components. So they are 9, minus 12, and 6, and 0. And I'm interested in what's the greatest common divisor of those. It's 3. And what I want to do is I want to take linear combinations so that I get a 3 there. That's okay. And then once I have a 3 there, then I can take multiples of that one and subtract or add it to these ones here to get those first components replaced with other vectors that have zeros. So I'm making the first components be mostly 0 except for a single fellow which has the greatest common divisor of that first, so the first column entries. So that's a success. So now what we can do? Now we look at the second column. We've kind of gotten the first column under control. So the vectors that we still have left are these 4. And the first column entries are 0, 3, 0, 0. So that's good. We can't do any better than that. In ordinary linear algebra, you might say, we can divide this row by 3 to make that a 1. We're not allowed to do that here. Okay, we're doing integer arithmetic. You can't generally divide by integers here. And in this case, we definitely do not want to divide integers because it can destroy our notion of integral linear span. We're going to get a different integral linear span. You can replace a vector by half that vector in general. Okay, so we move to the second column, and let's have a look at the entries. Well, aside from the one that we already have, the entries are 6, 8, and 14. And again, we're going to do a greatest common divisor calculation in our heads. That's not too hard. Greatest common divisor is 2. So what I want to do is I want to replace these things here with a vector that has a 2 in that second spot. Okay, so how do we do that? We want a 2. Okay, why don't we take row 7 minus row 6. What's the difference? That'll give us a 0, 2. That'll be our new row 8. Okay, what do we get to remove? We get to remove row 7. So there's an X there. Okay, but now we can get rid of this row. Just subtracting 7 times that. So we take 4 minus 7 times 8. That's going to give us 0, 0. That's your thing. And the 0, 0 we don't care about because we're going to ignore that. And the other thing that we want to get rid of is that 6. So let's take row 6 and subtract 3 times row 8. That'll be another 0, 0. Which hopefully not give that a number. And we're going to get rid of the 6. Okay. So the original 4 vectors have the same span as the vectors that are not crossed out on this list. What are the vectors that are not crossed out of this list? This one here, and these 2 zeros. But the 2 zeros don't contribute anything to the span. So we can conclude, therefore, the I span equals is the same as the I span of just the vectors 3, 1 and 0, 2. So if we have to, or wanted to draw a picture of this lattice in the plane, okay, using these vectors would be maybe onerous, okay? But now we can see it's relatively simple. There's the vector 3, 1 and the vector 0, 2. Those 2 vectors generate the lattice that we can draw pretty easily, and that is the same as the vector lattice that we started at the beginning. So you see the power of this, that we've been able to take a complicated initial description of an linear space and reduce it to a simple description because we found a good basis. This is now a basis for this integral linear span. So we have a minimal number of vectors that we need to span this space, namely these 2 vectors here. And I do want to just point out to you again before that the first non-zero entry in each of the vectors, this is the first non-zero entry, that vector, this is the first non-zero entry, they're both positive, strictly positive. And moreover, this entry here, which is in the second entry, the same as this, is less than that one. So it's positive in the sense that it's bigger than or equal to 0, and it's strictly less than entry 2. Okay, so the rules that we've used here, the essential rules for this integral row reduction procedure, are these following 3 allowed moves, let's say. Okay, so these are acting on multisets because officially those are the basic ingredients. I give you examples where we have vectors or vectors, but in fact, typically we have an M set of multisets, a bunch of multisets. And that's really at the level at which this procedure really operates. It really operates at the level of working with these multisets. Okay, although it's convenient for us to translate that into vectors because that is things with our usual intuition coming from linear algebra. Okay, so what are the 3 allowed moves? So V and U are M sets in our collection, and we're going to replace V with V plus K. So we're allowed to add a multiple of another M set to a given M set, essentially replacing it with what you get when you add another M set to it. It's a very simple operation. Here's an M set. I'm going to add something else to it, and something else could be a multiple of something else that's allowed to replace the original thing here with its sum with these copies of the other one. The second rule is to replace an M set by its negative. And the third one is to remove an empty M set. If at some point one of the M sets is an empty M set, well, this can't, because it's not contributing to the integral linear span. So I want to just quickly justify this one. We've seen this in special cases. The way the world is, the mathematical world. We say we're working with real numbers, and we actually work either in floating point or in infinite series or rationals. Anyway, in the usual linear algebra story, you're allowed to see a little more general here. You're allowed to replace v not just by minus v, but by any non-zero multiple of v. Like 2 times v, or 1/2 v, or minus 1/17 of v. Here we are not allowed to do that. Okay, so that's verboten in this story. Okay, so a little bit more restrictive. We're just sticking with integer, integral arithmetic here. So if you've understood this, it's not that far to understand Gaussian elimination in linear algebra. Okay, so some fun here for you, some exercises to really practice this kind of integral row reduction. So using only the allowed rules that we described, perform integral row reduction to show that the I-span of 10, 10, 15, 0, 0, 8, those three vectors, is the same as the I-span of 5, 2, and 0, 6. That the I-span of 4, 6, and minus 6, minus 9 is the same as the I-span of 2, 3. And here's a three-dimensional example. Okay, we have to just pop things up by one dimension, but it's the same kind of procedure. If you understood the idea, you should be able to figure this out. So the I-span of 2, 8, 11. So you end up getting the same as the span of 2 vectors. So you end up getting a situation where the lattice in question looks like this. It's not a three-dimensional lattice, it's really a two-dimensional lattice, even though it was generated by 3 vectors. So this is a typical subtlety here, is that you can't just look and say, oh, there's 3 vectors, this is going to be a three-dimensional lattice. You actually have to do some work to understand the geometrical nature of this lattice. Of course, this is all even more so in higher dimensions where our geometrical intuition and ability to visualize things is much reduced. Then you would have to work algebraically like this to understand what's really happening. And the final question, find a good basis for, so here's another three-dimensional situation. Here's 3 vectors, 4 minus 4 minus 2, 6, 0, 3, and minus 2, 5, 4. And I'm not telling you what a good basis is, you have to find one yourself. Okay, so that's really good. So what we're doing here is, we haven't really said it too much, but this is really Hermite normal form that we're getting at. So going from here, let's say going from here to here, it's really doing what's traditionally called Hermite normal form of a 3x3 matrix to get 2x3 matrix. And I want to talk a little bit about this procedure, make it a little more formal about what's happening, and frame it within our multi-set point of view. So it will be of this subject. So it's quite interesting. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening. Good day, I'm Norman Wahlberger. Today we're going to be investigating how the Hermite normal form helps us solve a lot of fundamental problems having to do with lattices in this relatively primitive approach to linear algebra and abstract algebra that we are developing here. So the definition is that linear lattice is the integral span of an M-set of vectors. We'll be talking rather generally about taking linear combinations of rather arbitrary M-sets. But when we restrict ourselves to vectors, then we get a particularly pleasant kind of situation which accords nicely with the usual linear algebra story. So let's agree that lattice is the integral span of an M-set of vectors. And we might use the adjective linear lattice if there's some ambiguity, and there is a possibility of ambiguity on account of that same term also occurring in combinatorics. So there's a poset lattice that we'll also be discussing at some point in the near future. Okay, so a lattice is really an integral version of what's usually called a vector space or a linear space in linear algebra. Usually, vector spaces or linear spaces are over fields, but these kinds of things are a little bit more elementary than that. They are sort of precursors to the somewhat more sophisticated coefficients of rational numbers. Here we're just taking integral combinations of things, so it's a little bit more in line actually with the general orientation of abstract algebra. Okay, and so here are 2 examples of lattices. Okay, the I-span of these 3 vectors, and I think just ordinary vectors if you like. These are vectors in 3-dimensional space. 6 minus 4 minus 7, 3, 5, 14, minus 3, 7, 16. These are 3 vectors, and all possible linear combinations is going to produce some kind of lattice. What kind of lattice it is, we don't quite know yet. And here's another one, we'll call it M, which algebraic span of 117 minus 9, 3, 3 minus 11, and 2 to 13 minus 11. Since this is not a course in abstract algebra, I don't want to go through all the details and layout theory completely precisely and completely, but I do want to give you enough of a framework so that you can understand and appreciate the logical structure of things. And so I'm going to be concentrating on these two lattices and talking about the theory in the context of these very explicit lattices so you can see what's going on. And the situation in general is not really that much different from what I'm going to be doing today. Now, we've seen that geometrically, lattices are actually relatively simple, depending on the dimension. There's really a relatively limited variety of possible shapes of lattices. The zero-dimensional lattice is just a point. That's a one-dimensional lattice is just something like this, or the extension of it in either direction, basically a copy of the integers. A two-dimensional lattice looks like an extension of this thing here. Okay, so it's here's the origin. Vectors, combinations, positive and negative, but always with integers. Okay, and then there's a three-dimensional version, something like this, where we have, say, starting from here, vectors going in three different directions, and we're taking again all possible linear combinations. So the geometry of any one lattice is relatively predictable once you know its dimension. But what we're interested in today is the relationship between the two lattices. There can be quite a lot more subtlety, because even though any one lattice is relatively simple, how two lattices interact is quite a lot more complicated, potentially. Okay, so we're going to think about our lattices L and M that we've described, and we're going to ask some questions. So first of all, we might be interested in a very fundamental question. That's a very key question, which is, are L and M the same lattice? They look different, we have different presentations of them, but perhaps they are in fact exactly the same lattice. So it's very important for us to be able to ask that question and answer it effectively. Otherwise, we don't really have a proper theory of lattices. Okay, is one of them inside the other? That might happen. That's the notion of a sublattice, where one is completely contained in the other, so that the vectors that we're starting with of one of them are all in the span of the other one. And if so, how to measure the separation, or how much bigger one is from the other? Is there some way of quantifying the relationship between the one that's inside and the one that's containing? And if not, so if one's not inside the other, there can still be possibly some interaction. In particular,